All right, good afternoon. Let's get started. So today just going to be a review. If we don't have a lot going on, we can finish a bit early. But well, we're definitely going to finish early, I think, no matter what. All right, if you have any questions, go ahead, please.
Like specific questions about problems or like general questions?
General questions or specific questions?
I was gonna say at some point, could we go over like a horizontal stretch, like vertical stretch? I guess I'm a little confused, like the difference between a vertical stretch and a vertical shrink.
So horizontal stretch. Sure. Yeah, we can look at some examples like that. That's mostly going to be related to exponential and the logarithmic in this part. All right. Any other questions?
I have some questions from the homework. If we could go over maybe just a couple from the homework.
Absolutely. Okay. All right. So let me go through a couple examples with horizontal and vertical stretch and the compression. That's related to exponential and logarithmic functions. I think you've seen them already on the quiz. So for exponential and logarithmic functions, generally, well, it depends on the situation. So exponential and log. It depends on what's given. So suppose we are given that f of x is equal to, let's just say 3 to the x, and a is 1 in this case. And then we're going to transform f of x to get g of x. And g of x is equal to, I'm just going to make it up like a negative 1/2 times 3 to the x minus 2. Right. So in this specific example, I did not really include any horizontal transformation there. To make it more complicated, let's say we're going to include the horizontal shift plus 4 to the x. So now we want to know what kind of transformation actually happened to f of x, which is equal to base 3 raised to the power of x, so 3 to the x. And maybe we're going to sketch a graph, or maybe find the asymptote, in this case, just a horizontal asymptote and domain range. So let's take a quick look. So for this g of x, and we know it's obtained from f of x through the following transformations. The first thing we can see is, well, this is 3 to the x, even though it's 3 to the x plus 4, but I can think about that as 3 to the x, like a 3 raised to a power, right? So what happened to that is we're going to multiply by 1/2. So that's going to be a vertical, because it's happening to the 3 to the x, which is f of x, happening to the entire function. So that's a vertical compression by 1/2. And then the -1 is going to be a vertical reflection. So it's going to be reflection over x-axis. And then the -2, again, is happening to the function f of x equals 3 to the power of x. So the -2 is going to be a down 2 units. And now we can talk about what happened to the x in there. So all the three I wrote already. So they're all the vertical, the changes to the y, but now we're going to look at changes to the x, which is +4. So that's going to be shifting left 4 units. So those are the transformations. And we can try to graph it. So suppose we're starting with 3 to the x. And it's exponential growth because b equals 3 is more than 1. And it's going to look something like this. And this point is going to be 0, 1. And then this is this horizontal asymptote at y equals 0. And suppose we're going to do all the vertical transformations first. So when we vertically compress by half, any point with y equals 0 doesn't change. So that stays, but the 0, 1 will become 0, half. And let's suppose there's a point here, so that's going to be compressed by half. So all the points on that curve is going to be compressed by half. So we get this curve that's half the height of the previous one. And then what we're going to do is we're going to reflect over the x-axis. When we do that, any point on the x-axis don't move, including the horizontal asymptote. So the 1/2 becomes -half. And that point is going to be reflected into the negative y-axis direction. So we get this curve. This is the -1/2, 3 to the x. And then we can move it down 2. So when we do that, everything will be shifted down 2 units, including the horizontal asymptote. So the horizontal asymptote was at y equals 0, but if we move it down 2, so let's see, this is -2, let's see, this is -1. So the horizontal asymptote will now end up at y equals -2. And the point on the y-axis, the y-intercept in the -1/2 will also be moved down to, so it becomes at -2.5. And that point also be moved down to, so we end up with this curve. -1/2 times 3 to the x minus 2. So that's all the vertical changes. As you can see, the vertical changes sometimes it affects the horizontal asymptote, sometimes it doesn't, depends on what the horizontal asymptote is. And the last part we have to do is shift it left 4. So if we move the whole graph to the left 4, y equals -2 is a horizontal line. When we move it to the left, it's still there. So that line doesn't go anywhere. And then this point on the y-axis, that has the x equals 0, but when we move it to the left 4, so that's going to go to left. Let's just say this is a 4. So that point is going to shift horizontally to the left by 4 units. And we just end up with this. We probably have a different, well, we're definitely going to have a different y-intercept here. And I'm not interested to find it yet. So this is the final graph, -1/2 times 3 to the x plus 4 minus 2. And suppose we're interested in the horizontal asymptote, we can find it from the graph, which is y equals -2. And suppose we want to know the domain. Well, it's the exponential function, so the domain is going to be all real numbers. And let's see, we want to find the range. As you can see, the range is very closely related to the horizontal asymptote. The range is going to be everything below -2. And it does not include -2 because it never touched -2. So that's going to be from -infinity to -2. So that's a range. And let's just see, for this particular problem, we want to find out what the y-intercept is, which we need to set x equals 0. Because the original y-intercept has been shifted when we move it to the left. So to find y-intercept, we're just going to set x equals 0. And if we do that, we get g of 0 equals -1/2 times 3 to the 0 plus 4 in the exponent minus 2. And if we are careful, 3 to the fourth power is not really divisible by 2, but we can calculate it. So that's about 81. So negative 81 over 2 minus 2. So that's a minus 4 over 2. So we get negative 85 over 2. So that's a y-intercept. And those kind of questions could relate to this exponential function. And I did not put a horizontal stretch and a horizontal compression that we could. And that's only going to affect the x, right? If you remember, if we multiply x by a number, we get this horizontal stretch or compression. For example, if we had, let's see, h of x equals, let's see, negative 3 to the 2x, for example. So now the exponent is 2 times x. So the x is being multiplied by 2. If x is being multiplied by 2, it's actually not a horizontal stretch by 2, it's actually horizontal compression by half. So remember, the x transformations is always going to be the reciprocal, the opposite of what the operation might suggest. So this is going to be horizontal compression by 1/2. So suppose we still had that graph with this horizontal asymptote. This is, I should move it up a little bit to show the difference. So this is the 1. And let's just see, we have another point for y equals 3 to the x. X equals 1, y equals 3. Oh, I'm not drawing it to scale. You know what, let me fix this. So this is the 1, 2, 3, 1, 1. So that was my sort of parent function, y equals 3 to the x. And then we want to know how is this h of x related to this parent function. The negative, again, is just reflection over x-axis. And the 2, it's going to, we said that's a horizontal compression. So if we were to graph it, so if we reflect over the x-axis first, so we get this -1, +1, 3, and then we get this 1, -3, 1, 2, 3. So we get this graph when we reflect it over. -3 to the x. And what about the horizontal compression by half? Well, that's just going to take every x value, we're going to multiply by half, but keep the y the same when we perform the horizontal compression. So the 0, -1, x is already 0. So when we multiply x by half, it doesn't change. The 1, -3. When we compress horizontally, just going to move it close to the y-axis. So this point has x coordinate 1. So when I compress it by half, that point is going to have an x coordinate half. The y coordinates stay the same. And let's just say, suppose we have on the left, there was another point, -1, 1/3. When we reflect it, that becomes a -1, -1/3. When I compress that by half, so that's going to be -1/2, -1/3. So now we have this 3 new points with the point on the y-axis stay the same. So I'm going to use a different color. So we get this new point here, this point, and then this point. So if I were to graph it correctly, so I get this graph. So that's a horizontal compression by half. It's not quite the same as a vertical stretch because the graph, if you think about horizontal compression, when we squeeze towards the y-axis, The left side, as we move towards y-axis, the y value is kind of getting closer to the x-axis. The right side is kind of getting closer to the y-axis, means it's away from the x-axis. But if we perform a vertical stretch, all the points will be away from the x-axis. Okay, so that's that one. And another example on logs. So suppose we have, suppose we have f of x equals 2 log base 5 of x minus 1. So that's f of x. And I want to take this function and transform it to get g of x. So g of x is obtained through transformations on f of x. That's the following. So we're going to take f of x. We're going to do a few things. The first thing we're going to do is we're going to move it down 3 units. The next thing we're going to do is we're going to take whatever we have. We're going to reflect over x-axis. It's a vertical reflection. And then the next thing we're going to do is we're going to move it to the right by 2 points, 2 units. So I want to know what the formula for g of x is. So formula for g of x. Well, let's just take f of x and we're going to follow exactly what the steps tell us. So this is what I'm starting with. I'm starting with 2 log base 5 of x minus 1. So the first thing is when I move it down, so I'm going to take whatever I have, I'm going to subtract 3 because when I move it down, I'm affecting the y. So that's a 2 log base 5 of x minus 3 minus 3. Sorry, x minus 1 minus 3 at the end. So that minus 3 is affecting this piece. And then the next step, I'm going to reflect over the x-axis. If you remember, reflection over x, it's going to make the y opposite. So if this is my y value, when I reflect over the x-axis, I'm going to end up having a negative in front of it. And then the last step is move it right to. So when I move it to the right or left, it's only affecting the x. So the y part doesn't change. So the negative, the 2, the negative 3 doesn't change. But inside the parentheses, the x minus 1 will be different. So when I move it to the right, so I'm going to actually subtract 2 from the x part. So that's going to give me negative 2 log base 5 minus 3. And the x minus 1 will have x minus 1 minus 2. So the second minus 2 means we shift it to the right by 2. And then the next is just rewriting everything, simplifying, distribute the negative in the front. So we get negative 2 log base 5 x minus 3. And then negative negative becomes positive 3. So this will be the formula for g of x. Any questions on those? A related question could be, what is the asymptote? In this case, with logs, we're going to have vertical asymptote. What is the domain? What is the range? So if you remember for log function, when we want to find the domain, or when we want to find the vertical asymptote, we're going to look inside the parentheses. So vertical asymptote will be given by x minus 3 equals 0, x equals 3. And the domain is going to be that expression, x minus 3 has to be positive, x greater than 3. So you have vertical asymptote here, the domain either going to be to the right side of it or left side of it depends on whether we have a horizontal reflection. We don't. So the graph probably going to be on the right side of that vertical asymptote. And could be asking about range. Now the range is always going to be all real numbers for log. Okay, and in this question, I'm not asking about the x-intercept. If I do ask about the x-intercept, we're just going to set y equals 0 and try to solve for x. So if it's asking for x-intercept, we can set y equals 0 or g of x equals 0. Try to find x from there. So we get -2 log base 5, x minus 3 plus 3, set it equal to 0. So move the 3 over, divide by -2. -2 log base 5, x minus 3 equals -3. And now we divide by -2, so we get log base 5, x minus 3 equals 3 over 2. And from here, we're going to have to solve for x, right? Now, I think this is a good practice to solve logarithmic equations. To solve for the x, we're going to somehow get rid of the log base 5. So there's a few ways. Either we can convert it to exponential expression. So that will be the base 5 is still the base 5. And then this part next to the base 5 and then this part away from it. So they're going to switch. So we get 5 to the 3/2 is equal to x minus 3. And then from here, we're adding 3 to get x by itself. So we get x equals 5 to the 3/2 plus 3. So that's one way. So you can quickly check that's a valid answer, because if we put the x value in there, x minus 3 is equal to 5 to the 3/2, which is positive. That's a good thing. That's to check. So that's one way. Another way is just adding a base 5 to both sides of the equation. So let me rewrite what we had. We had log base 5, x minus 3 equals 3/2. If I want to get rid of the log, I'm going to add base 5. So I'm going to add base 5, converting both sides into exponential expression. The left side, base 5, exponential base 5, and a logarithmic base 5. So that cancels, give me just x minus 3. And the right side, I get 5 to the 3/2, and adding 3 from there, give me the same expression. All right, any questions about those examples I went over so far?
So if you were to do like a horizontal stretch to say -2 log 5 x minus 3 plus 3, would you just be putting a coefficient in front of that x for that? Or
that it's a little bit tricky. Because it depends on the way we're written. So with the horizontal transformation, if you have so here we have, so log base 5 of x minus 3 already. So this -3, I can think about that's a shifting to the right. So this is a shift to the right by 3. So that's already happening. So let's say I have this, and then I'm going to add a horizontal stretch by 2. And where do I put the 2? Do I put it in front of the x directly, or do I have to put everything in a parentheses first? So here's the 2 things. One is, does it look like 2x minus 3, or does it look like log base 5 of 2 parentheses x minus 3? Right, so that's something we have to be careful. I don't imagine I'm going to give you a problem like this, but that's a very good point. I just want to use this opportunity to explain quickly. With the horizontal operation, so here we have a multiplication and a subtraction in this part. Normally, we put multiplication first and then subtraction in a regular operation. But with horizontal transformations, we have to do the opposite way. So if it's written 2 times x minus 3, that has the order of the one above. Is actually, we're going to do the subtraction first, which is shifting to the right. And then we're going to stretch the multiplication. So it's opposite from the order of operation. But if we have 2 times parentheses, so here we have a multiplication and a parentheses. Normally we do the parentheses, x minus 3, but in terms of horizontal transformations, what we're going to do is we're actually going to do the multiplication before the parentheses. So that's going to be multiplied by 2. So that's a horizontal stretch by 2 first, and then we're going to do the parentheses part, x minus 3, which is shifting to the right by 3. So that's the difference with horizontal transformations when you have stretch and shift all together. But Jonathan, to answer your question, you had that your point was correct. So if we take what we have and then we add a horizontal stretch, we just literally can add a 2 in front of the x. But let's see if I give you something like let's say log base 5 of x, and I'm going to tell you, okay, so I'm going to do horizontal shift first, and then I'm going to do a horizontal stretch. So that will be the first case. But if I say I'm going to do horizontal stretch first, and then I'm going to do a horizontal shift, we have to put into the form with the parentheses inside the log. So that's something we have to be careful with horizontal stretch and the shift combined. Like I said a couple of minutes earlier, I don't think you need to worry about those two transformations together. It's not going to be on the exam. But when we have a vertical transformation, let's say you have a vertical shift and then you have a vertical stretch, just follow whatever the order is.
All right, cool.
Okay.
Thanks. I think that answers my questions.
Yep, very good question. Okay, let's see. Any other questions related to those examples? All right, Ryan, let's go through some questions from the homework. Which one do you have on your mind?
Yeah, so the one that I'm looking at right now is natural log of y times the square root of y over 4 minus y.
Sorry, I didn't catch what you said. The second.
It's okay.
Natural log of y times square root
of y over 4 minus y.
Like all underneath the square root?
Yes, just like that.
Is this question about rewriting it?
It's rewrite it as a sum difference or product of logs. Yeah.
Okay. 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 So here, if we just look inside the log, we have a product that's jumping up, and then that's a y times the square root part. So let's apply the product rule first because that's what's obvious. The product in there. So that's going to be natural log of y plus, every time we have a product in the log, we become sum of 2 logs. Natural log of square root y over 4 minus y. Right, so the first part, just the way it is, nothing we can do. Now the second part with the square root, we can't do anything if we have a square root there, but we can rewrite the square root in terms of exponent of half. So I'm going to leave the first term. And the second term, I'm going to rewrite it as natural log of y over 4 minus y to the half. That's all inside the natural log. And the good thing about exponent half is that we can actually put the exponent to the front of the log. So that's using the exponent property with the log. And again, the first term stays. Now I can bring the half in front, so that becomes half times natural log of whatever remaining y over 4 minus y. And now if we look inside the second natural log, I have a division, a quotient y divided by 4 minus y. So that means I can use the quotient rule. So that's going to be plus 1/2. Well, I have to be careful because there's a 1/2 times the log, right? So doesn't matter how I rewrite the log, the natural log in the second part, I have to multiply the result with half, the 1/2 times natural log quotient rule become a subtraction, y minus natural log of 4 minus y. And now I can try to simplify because I have a natural log of y in front, then I have half natural log y if I distribute the half. So let me put this back. So I get natural log of y plus 1/2 natural log of y, distributing the 1/2 there, and then distribute to the second term, minus 1/2 natural log of 4 minus y. And the first two terms I can combine, right? So that becomes 3/2 natural log of y minus 1/2 natural log of 4 minus y. There's nothing we can do. If we have a subtraction or addition inside the log, don't do anything. Nothing can do here. Only if we have a product, a quotient, a exponent in the log, that's when we can rewrite it, not with the addition or subtraction. Sorry, nothing for here, for this part. Now some of you probably think, okay, can I rewrite the part inside the log first by replacing the square root with half exponent and then distribute the half in the exponent and then combine with the y in front of it before applying the properties of logs? That's totally fine. I think in the end, you end up with the same expression. Okay, anything else?
That looks good for me. Thanks.
Oh yeah, no problem. Let's see, any other questions or anyone else have any questions? That's it. No more questions from anyone else? All right, think about it. If you have more questions, let me know. There's one thing that I've been debating if I want to talk about it or not. I feel like I should talk about it at least. For some of you, you might find it like interesting, at least to know about it, because you might come across it in a different class in the future. So the next thing just one more thing to cover here is angular velocity. Oops. And also linear velocity. And we are all familiar with the velocity, right? If we have a particle traveling on a straight line, and And then we can calculate how fast the particle moves by finding the distance and divided by time. So that's the speed, or if we consider the direction, that's a velocity. But what is the angular velocity? Well, then in that case, we can consider a particle is traveling on a circular pathway. So let's say it starts here and it moves. And as it moves, it's going to cover an angle. Let's say it's starting here, and as it moves, let's see, after a time t, and it's going to travel this, in terms of the angle measure, it's going to cover this angle theta after time, some time, and that angle covers in the given time, we can use it to find angular velocity. So angular velocity measures the rate of angle rotation per unit time. So suppose the particle traveling on this circle, and it's, let's see, after t seconds, is cover this angle theta. So the angular velocity, this omega, sometimes w, is equal to theta over t. So it's really just the angle divided by time. When it comes back to the regular velocity traveling on a line, we talk about a distance on that line divided by time. So here we just talk about the angle divided by time. So that's angular velocity. Linear velocity in this case, or linear speed. So linear velocity in this case measures the distance, or sometimes I like to use length, traveled per unit time. If we strictly talk about the particle traveling on the circle, the distance or the length it covers is actually not a regular distance that we talk about on a straight line. It's actually the arc length. So the distance traveled is actually the length of the arc. So we're going to use V in this case. So this is the V, is equal to S over T. S is arc length, and the T is time. So you can think about arc length as just some distance, but on a circular curve rather than on a straight surface or straight line. So that's the difference between angular velocity measures how quickly does the angle change, and the linear velocity measures how quickly does the length change. And then we can rewrite this. We can rewrite this linear velocity if we plug in what the arc length is. So if you recall that arc length S is equal to R theta. And if we put this in there, we get this linear velocity, which is R times theta divided by T. And the theta times theta divided by T is omega, the angular velocity. So we get R times angular velocity, omega. So that's just another formula for linear velocity that relates linear velocity to angular velocity, just radius times angular velocity. So here I have an example. So suppose a bike will let's see, a bike wheel with diameter equals 30 inches. Completes, so the bike wheel completes 2 revolutions in 5 seconds. And then we want to know the angular velocity. And then we also want to know the linear velocity. So suppose the bike is, we're riding the bike as the wheel spins, we cover a distance on a flat surface. And linear, so the distance, the speed that covering the linear distance, that's the linear velocity. Okay, so that's all we know. And we don't know how much the angle amount was covered, right? And all we know is that the bike wheel covers 2 revolutions in 5 seconds. And we know the diameter of the bike wheel, which is 30 inches. So we know the diameter is 30. And we know that, suppose that's a center. So as it rotates, it makes 2 revolutions, 2 rotations in 5 seconds. So in this problem, so let's see, we want to find the angular velocity. That's going to be the angle traveled divided by time. And I know that time is 5 seconds, but I don't know the angle, but I can find it because 2 revolutions, 1 revolution is a full circle. So 1 revolution is equal to 2 pi. And the 2 revolutions, that's going to equal to 4 pi. That's how many radians 2 revolutions are. So that's the angle. So that's going to be 4 pi radians divided by 5 seconds. So that will be my angular velocity here. And I suppose I want to find the linear velocity. So I have to figure out what's the length of the arc or the length on the circle does it cover for 5 seconds. So we can either use a shortcut, the V equals R times omega, or we can take the long way, which is S divided by T. Either way should work. So let's see, we take the long way. So the linear velocity on the circle is going to be S divided by T, and S is arc length for 2 revolutions. So that's really just 2 circumference, right? So that's 2 times 2 circumference, 2 pi times radius. Radius is 30 over 2, the diameter over 2. And then divide by time, 5 seconds. And if I simplify this, so that's going to be 2, so that's 30 pi times 2, that's 60 pi over 5. And that's going to be 12 pi. Now, because the diameter is in inches, so this is going to be inches per second. So that's the angular velocity and the linear velocity in terms, the linear velocity is related to the arc length, the distance traveled on the circle. Let's just suppose we want to double check. Let's see, we use the second formula. The linear velocity is equal to radius times the angular velocity. So the radius is going to be 30 over 2, 15, times 4 pi over 5. And that's going to be 15 times 4 pi over 5. 5 cancels. That's going to be 3 times 4. That's a 12 pi. So we get the correct answer for both methods. Anyway, so that's just the angular velocity and the linear velocity on the circle. I just want to talk about that. So think about the way I try to think about it, angular velocity related to the angle. So it basically measures how quickly the angle moves. Linear velocity measures the distance. That's a traditional velocity, right? Distance over time. But on a circle, you don't have this like a straight line, a straight distance. So that's why we have to use the arc length on the circle to represent the distance. And that was the last thing that I wanted to talk about. Okay. All right. Anyway, so let's go back to questions that related to the exam, or just any other general questions. Well, if you don't have questions, we might have to end early. But I do want to use this opportunity to let you ask questions.
Question.
Yeah, go ahead, Brian.
Oh, is this upcoming exam going to cover everything since last exam or the last quiz?
Since last exam, so that will be from section 4.2 all the way to section 5.2.
All right, thanks.
Yeah.
I don't have any questions now, but if we do have some in the future, should we just email you?
Right. Yeah, just email me. Yeah, that should work.
Okay.
And I think I have office hours Monday, but if you have questions before that, I think I also have office hours tomorrow. I may or may not be there, but if you email me, say, can I ask you questions tomorrow during this office hour time, I'll make it there.
Okay. Thank you.
Yep, no problem.
I have a question.
Oh, go ahead.
So it was about a question on the homework.
Okay. Yep.
It was about finding carrying capacity.
Okay. Do you have the number, the problem
Yeah.
number? That's,
Yeah, so it's 130 divided by 1 plus 7e to the negative 2x.
70 to the negative 2x?
7e
Oh.
to the negative 2x.
Okay, good. So if you have a formula given the carrying capacity, if you remember what I wrote yesterday, the general formula for logistic growth is C over 1 plus A times e to the negative bx, right? So the C in the numerator is the carrying capacity.
Oh, is that all it is?
Yep.
Oh, thank you.
Mm-hmm. So related to that, so if you curious whether you need to memorize the logistic growth formula or the Newton's law of cooling formula, you don't have to memorize those. If I give you a problem like that, I'd probably just give you the general formula. That's the f of x equals this, right? I'm not going to give you you're going to have to figure out what each of the constants should be in a given problem. But I'll provide this general formula to you if you do need to use it. And let's see, in this since last exam, we talk a lot about exponential, logarithmic, and a lot of problems, maybe it looks like a calculator problem, right? You can definitely solve them with a calculator. Just leave your answer in terms of natural log or in terms of exponential. Let's see, let me ask you this. Does it make it easier if I allow you using a calculator on this exam? Any preference?
Yeah, I think it would.
That would be easier.
Yeah,
All right,
it saves time to not do like everything up by hand.
Yeah.
right. Okay, that's totally fine. So let's see. Yeah, let's make this calculator okay on this exam. That's not a problem, because a lot of problems with logs and exponentials, we're probably going to use calculators in anyway when we encounter them in other examples. Okay, so let's see, calculator is okay. suppose, let's just say, you know, for whatever reason, when I write the exam, I forget to change the instruction. The instruction probably says no calculator allowed. Just ignore that part. Feel free to use a calculator if that does happen. But I would say don't. So obviously, you know, let's just say you don't have a graphing calculator with you. You just want to look it up what the natural log of 5 is, right? You just need to know that number to make it easy. Or if you want to use the calculator, I don't know, on Google or whatever, or on your computer to calculate, you know, 5 times 1.765, something like that. That's totally okay, but do not look up the problem. So if I give you a problem, don't just say, oh, I'm going to type this into whatever the, you know, the best way to get the answer online. Don't do that. That's not benefiting you. But again, that's your choice if you do decide to go down that path. Anyway, so that was a comment on that. So still not allowed to use textbook notes, talk to your friends, none of that, but you can use a calculator. Anything else? Actually, you know what? Let me say one more thing about the use of calculator. There's one specific type of problem I don't want you to use the calculator. For example, if it says find exact value of sine, let's just say negative 270 degrees. This type of problem, I don't want you to use a calculator. I'm going to actually tell you not to use a calculator. Don't use calculator. For a problem like this, what I want you to do, I want you to graph the angle, negative 270, and then use the unit circle there. So this is my unit circle, and graph the angle negative 270. So this is a negative 90, negative 180, negative 270. So it ends up here. So we're going to use this point. In order to find sine, I have to know the y coordinate of that point. So sometimes you might have to draw a right triangle to get the two sides, two legs for the right triangle. But in this case, we don't need it. So let's just say the coordinates for that point is going to be x equals 0, y equals 1. So therefore, sine negative 270 degrees is equal to 1. And then suppose we have an angle that doesn't end up on the y-axis. So let's see, suppose I give you sine of Hmm. 510. I hope it works. Suppose this is the angle we want to find the exact value for. So we have to graph it first. So that's going to be 510 minus 360 degrees. So that's going to be 150 degrees. So if I were to graph the angle, I'm going to go from this positive x-axis, we're going to go a full circle, but then go back, keep going until we reach 150. So it's going to be here. So the angle here is 510 degrees. And from there, I'm going to create a right triangle using the x-axis. And this reference angle, the angle between the terminal and the x-axis, so this small angle here, that's going to be 30 degrees. So let me make this look bigger. So the angle there, the reference angle is going to be 30 degrees. So I get this 30, 60, 90 right triangle. And I can, if you remember the special right triangles I had yesterday, so the hypotenuse is 1. And the side opposite from 30 is going to be 1/2. The side adjacent to 30 is going to be √3/2. And I'm looking for sine. So that means I'm looking for the y coordinate for this point. X is cosine, y is sine. So the y coordinate is like how far do I go up in the y direction? Just half unit in the positive y direction. If I want to find the cosine, I can find x. It's how far does it go in the x direction from the origin? It's √3/2, but negative in the negative x direction. But in this case, I'm interested in sine, so that's going to be 1/2. But suppose I'm interested in cosine, 5, 10 degrees, and I expect a value of negative √3/2. But if you use a calculator, you're probably not going to give me negative √3/2, right? I don't know. The calculator might give me some number that's correct. It's a correct estimation, but it's in decimal digits. That's not the one I'm looking for. So just be careful when you work on problem like this type. So let's just say you type cosine 510 degrees into the calculator, it give you, I don't know, negative 0.8 something. And I'm not going to take that as the valid answer when I ask you to specifically find the exact value and do not use a calculator. Does that make sense? Okay. So just pay attention to the instructions on problem of this type. There's certain problem that you have to use a calculator. For example, if I say, okay, calculate the cosine of 51 degrees, right? I don't know how to find it by hand. So that's perfectly fine to use a calculator, but I'll be specific for certain problems there. Okay, any other questions? All right, I just want to make another comment about homework. I think I'm actually just on that homework page now. Let's try. So if you, I hope that you don't need an extension because you do need to, look through the homework problems so you're more prepared for the exam. But suppose, you run out of time, you want a little bit more time, you can click on request extension. And if you click on it, it should show up. It says manual or automatic. It says manual extensions are not active for this assignment, but if you click on automatic, but then it says automatic extensions are only available for past due assignments. Well, anyway, try to figure out a way to get extensions. So it should be able to, I cannot get the automatic extension to work on my end, but you should be able to get it to work. All right, give it a try. If you run into problems, don't panic, just email me. Okay, final question. Any other questions? Or anything else? Just like the previous one, on Monday, you don't have to show up. The exam will be available at 6:10. And again, you have all the way until 8:30 to work on it. Then you have extra 10 minutes to scan your work. Make sure you double check. You scan all the pages, right? If you miss a page, that's gonna, I don't know. I'm probably gonna ask you to send me that page, but I don't like doing that. So after you submit it, definitely make sure that all pages are uploaded and submitted, and that way, we can avoid some troubles between us. Okay, anything else? Okay, it's almost 7:10. We're just going to end early. It's just a review today, just exam review. But anyway, good luck studying, and let me know if something shows up. And good luck on the exam on Monday. All right.
Thanks.
All right, take care, everyone.
Take care.
Goodbye.